Okay, one-day growth factor. Alec. What's the one-day growth factor for this situation? Okay, this is key. Gotta know this to be able to do anything in this unit. Walter.
One-day growth factor?
Yep.
I thought
1 point what?
568.
It's not 1.568. 1.45. The bacteria grows 45% every day. And so back from 2 weeks ago, and ever since then, we've been working with these growth factors. The multiplier then would be 1.45 to get how many bacteria would be the next day if it's increasing by 45%. Okay, population after X days. Buddha.
630.
That's it. Okay, and then how do we get the number of bacteria at 10 days? Anna. Yep, f of 10. That's f of 10, right? That's would be our way to represent the number of bacteria at 10 days. The output when the input is 10. The output when the input is 10 is f of 10. So how and why does 630 times 1.45 to the 10? Why does that give you the number of bacteria on the 10th day? What's going on there in that calculation that makes sense that it would give us the bacteria on the 10th day? So everyone get a partner and discuss that question. Everyone's got a partner. So there's going to be 20 conversations in here, okay? Why does that calculation give the number of bacteria on day 10? Why does it make sense? What do we think? So, Austin, can you explain why does that calculation make sense to give us the number of bacteria at 10 days? Right? 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 Well said. Okay. All right, so let's bring it back to the front. So what he said was 1.45 is the one-day growth factor. If you multiply it by itself 10 times, it gives you the 10-day growth factor. And so if you multiply that by some number of bacteria, it'll give you the number of bacteria 10 days later. Well said. Here's another way to think of it. Okay? So 630 on day 0, if I multiply it by 1.45, what does that give us? How many bacteria on day 1, right? The number on day 1. And if I do that again, the number on day 2. Because the growth factor is the multiplier on some output, it'll give you the next output. In this case, bacteria on the next day. So we're going to multiply by 1.45 10 times. And we just have a shorthand way of writing that. Right? So multiplying by 1.45 10 times is 1.45 to the 10th. Okay, so that's all review from the beginning of the unit. This is the basics, and everything we've done has been built on this idea. Okay? All right, so same situation, new question. How many days will it take the population to grow to 500,000 bacteria? So where would we start? Where would we start analyzing this or making progress? Justin?
Well, you know that the final population is going to be 500,000, so you'd set that equal to the function.
Okay, and so is that input or output? 500,000. Is it input or output? Be the input. Alex. Yeah, so that it would be what you get, what the function gives us, the output. And then, yep, so that f of x would be the output. And so how many days is the input, right? How many days is the input? Okay, so doing that, we get this. And our goal is to figure out what x is. So we could do a first step of algebra here, divide by 630. And here we are, 793.65 equals 1.45 to the x. Okay? And solving this equation for x, figuring out what x makes that true, is then going to give us how many days it will take to reach 500,000. Okay, but in terms of having some kind of algebraic tool to do this, you know, what do you do to both sides? Well, there's nothing you can do to both sides to solve for x, like subtract something from both sides or divide by both something. So we've kind of got, how do we solve for x? We kind of have a situation here. How do we solve for x? So what we do is we think about what exactly is x. Okay? So here's a way to describe x. Would you agree that x is the exponent of 1.45 that gives 793.65? Would you agree with that? Perfectly fair statement. Okay, so mathematically we have a way to kind of write this in a compact form. Okay? We have a way to write this in a compact form, and that is a log. So rather than write out the statement, the exponent of 1.45 that gives 793.65, this is equivalent to that. This is equivalent to that phrase right there. Okay? So what are we saying? So you may have seen logs in the past, and you may think of them as it's a method or a way to solve for exponents. Okay? But I want you to hopefully adopt a different view than that. What are we really saying a log is? Is it a way of solving for an exponent? What are we saying? No, it is an exponent. A log is an exponent. Logs are exponents. That's the way I hope the way of thinking I hope that you will adapt. Because as you'll see, it's a very helpful and beneficial way to think about it. Rather than just a log is a tool or a method. No, logs are exponents. That's what they are. So this particular log, the log base 1.45 of 793.65, what is that? That is the exponent of 1.45 that gives 793.65. So let's kind of flesh this out. All right, and so that particular log or that exponent turns out to be 17.97 days.
Usually,
We'll get to that later. What's that?
wouldn't you usually just use a graphing calculator?
That's what I told you. So up to this point, yeah, graph that function and then look for where it hits 500,000, what x value hits right. But now we're talking about having kind of a more numerical way of solving that question, and that's where logs come in. Okay? All right, so we'll get back to this, getting this actual number, 79.97, from this log notation. We'll get to that a little bit later in class. But we want to just really understand the basics here of that logs are exponents. So here's this expression, and so it's equivalent to this expression. Both of those mathematical expressions say this. They both say the exact same thing, that x is the exponent of 1.45 that gives 793.65. Both of those, so let me show you how both of those say that. So in the first one, there it is. X is the exponent, right, of 1.45. That gives 793.65. Makes perfect sense, right? There it is. X is the exponent. Should be using this. X is the exponent of 1.45. That gives 793.65. What about on the right? Here we go. X is, and if logs are exponents, then this is it. This is the exponent of 1.45 that gives 793.65. So this is the way that we want to view logs. That when you see a log, you think of it as what this phrase says right here. The exponent of whatever the base number is, that gives whatever that number on the right is. Okay, so, and then the way we say that is, the language is the log base 1.45 of 793.65. But the meaning is the critical part. Okay? So we're going to practice this with easy examples. Okay? Because those who have had logs before, you may be kind of trapped in a mindset of it's algebra. You do this, you move this thing here, you shift these, right? So rather, we want to really get to practice seeing it as the idea, okay? So for each log, first you're going to describe in words exactly which exponent it is. Then write the description as a mathematical statement. So the words that you describe, that you use to describe which exponent it is, will then help you to set up a mathematical equation. Okay, so for instance, here we go. So A is the log base 5 of 25. So any volunteers? What exponent is A? What exponent is A? Can you describe which exponent A is? Brooke. She said A is the exponent of 5, which gives you 25. What do you think? Okay, and look, it's so easy because you can just read this left to right. You can just read it left to right. It's the exponent of 5 that gives 25. It's the exponent of 5 that gives 25. And that's A. So if A is the exponent of 5 that gives 25, what equation can you set up? Christian, if A is the exponent of 5 that gives 25, what can you say?
5A equals 25. 5 to the A equals 25.
He wants 5 to the A equals 25. Yeah, that's exactly what that phrase says, right? What that phrase says is that A is the exponent of 5 that gives 25. And so, therefore, what is A? 2. We know that 5 squared is 25. So, the log base 5 of 25 is 2. Because we're talking about the exponent of 5 that will give you 25. Okay, practice. So you got one now. Practice. First thing you're going to do is describe in words what exponent that is. From your statement, build the mathematical equation. Describe in words, then from your description, build the mathematical statement. Okay, Nina, tell me.
Z is the exponent of 2 that gives 16.
She wants Z is the exponent of 2 that gives 16. Okay, so, Shola, what's a mathematical statement we can set up that reflects that Z is the exponent of 2 that gives 16? That's it. And so now you can look at it in this particular, so we can say, what is Z? 4, right? So what is 4? 4 is the log base 2 of 16 is 4. Because we're talking about, that log is talking about the exponent of 2 that would give you 16. Another practice. Does this make sense? Go. Audie, what exponent is p?
P is the exponent of 4 that will give you 164.
That's it. Tell me then, how can we set up a statement that reflects that?
You put 4 raised to the P is 164.
Nailed it. So now if we want to figure this out in our head, we need to kind of get apples to apples here. So I've written 1 over 64 as 1 over 4 cubed. That will give us kind of a way to get p just by thinking about it. And so what would p be? He wants negative 3. Negative 3, that's it. So the log base 4 of 164 is negative 3. Again, because we're talking about the exponent of 4 that gives 164. 1/64. Any questions? All right, let's just practice one where we have to kind of estimate. So how about the log base 3 of 17. So
Equals to what?
so does it, so does it make it any less of an exponent since it doesn't equal a variable? Okay, so you make one up, right? So Hamid, what do you want it to be equal to? A. So you get to choose, right? So it doesn't make it any less of an exponent if it doesn't have an equals some unknown, right? All right, keep going. So what exponent is A?
The exponent of 3 that gives
Right. A is the exponent of 3 that gives you 17. And so how about the math that backs that up?
17 to the power of A equals to 17.
And so A is the exponent of 3 that gives 17. That's what you told me.
3 to the power of A that equals to 17.
Yeah. So when you say that statement, you gotta listen to it. Okay. So now, can we estimate? So this isn't a whole number, right? So, but can we estimate what A would be? What would you guess A to be?
Yeah, fraction.
Okay, but what? Like, is it 10? Is it 1.1? How can we?
2.5.
What's that?
2.5.
He wants 2.5. Why, Christian?
Because it's halfway, 17 is halfway between the square of 3 and the cube of 3, which is 27 and 9.
So square of 3 is 9. Cube of 3 is 27. And he's saying, oh, look, it's about halfway between those two. So the exponent, you're saying, would be about halfway between.
Yes, somewhere 2.4.
Okay, so what we need is, so we've got this log, so log base 3 of 17 is about 2.5. So we need a way to get it exactly. So we want to use our calculator to get that exactly. So we'll put that question on hold for a second, and I want to show you something more about logs and calculators, and then we'll come back to that. Okay, so that's what we want. So we're thinking it's somewhere between 2 and 3 toward 2.5. Well, can we get it correct to several decimal places using our calculator? So sometimes you will see this. That's what you'll see. So what's going on here? So it seems like this is missing, right? This is missing. So yeah, so if nothing is there, the implication is that it's 10. The base is 10. Okay, this is called common log. So, who can describe this? What this means right here? Log base 10 of 10,000. Who can describe that? Somebody new. Patrick, what is log base 10 of 10,000 in a phrase?
Saying that the exponent of 10, so 10 to the exponent x, equals 10,000.
He's saying that log is the exponent of 10 that gives you 10,000. Agree? So what is that number? 4. So the log base 10 of 10,000, or just the log of 10,000, if there's nothing there, 10 is implied. And so this would be 4. Okay, that would be 4. That's called common log. Common because our number system is based on tens, right? Our number system is based on tens. And so it's a very common log. That's why it's called that. All right. Another one you'll see is this. This is ln, lowercase l, lowercase n, ln. Okay, that's a shorthand for base e. So all natural logs are what kind of numbers? All natural logs are what kind of numbers?
Exponent.
Of what?
Of e.
They're always exponents of e. Natural logs, by definition, they're log base e, so they are exponents of e. That's what natural logs are. They're always an exponent of e. So this particular one, what exponent of e is it? Brian?
E to the x equals 24.
So it's the exponent of e that would
Well, give you 24.
give you 24. So the exponent of e, if this thing is, he's calling it x, let's call it x. That thing is the exponent of e that will give 24. Okay? This is called natural log. Because e is called the natural base, and we talked about e last time. You saw e in your video over the weekend, and then we talked about e on Tuesday. Okay, so these are the most frequently used and prevalent bases for logs. So your calculator has buttons for each of these. So most of you have the TI-83 or whatever. So on the left-hand side, you've got just the log button and then the ln button. So put in log 10,000. So put in log, hit log 10,000, and you should get 4. Do you get 4? Okay, and remember that E is 2.71828 ... So can we estimate the exponent? What exponent of 2.71828 blah 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 might give us 24? That's a little harder than the example I had before. But so this is almost 3, right? And we know 3 cubed is 27, but our number is a little bit less than that. So what x might be around 3, right? You see that? So because we got a little bit less than 27, and our base is less than 3. So maybe x is around 3. So do ln of 24. What do you get? Close to 3? What is it? 3.18. Okay? So ln of 24 is what? The exponent of e that would give 24. Okay, so what about other bases? So I gave you, what was the example I gave you earlier? The one we thought was about 2.5?
3, you have 3,
Uh-huh.
17.
The log base 3 of 17?
Yeah.
So you don't have there isn't a single button on your calculator that does log base 3 or log base 11 or log base 2.8, okay? These are the ones that have a built-in button. So in order to solve something like this, log base 3 of 17, there is what's called the change of base formula. What you can do is you can rewrite any log as a log with any base that you want of 17 divided by the log of the same base of this number 3. So as long as you choose the same base for the numerator and the denominator, that quotient will equal this value. So what are you going to choose? Yeah, so you're going to choose one of the two that you have a button for. But both will give you the same answer, so we're going to do it both ways. So we're going to do log of 17 over log of 3. And what was our prediction for this? I think Christian said 2.5. So do log of 17 over log of 3, and then do ln of 17 over ln of 3. Change of base formula says when those bases match, you get the same, you'll get this answer. Say it again? Yeah, it's like in a menu or something, right? Yeah. But if you had a more simple calculator that didn't have that, but you had just log, then you would need this. Yeah. If you want to use it, that's okay. Yeah. Okay, what do you get when you do that? How's our guess? 2 point what?
2.5. Yes.
Right, but what do you actually get? Nice and loud. 2.5789? 2.579. About. Does it work the same way when you do ln? You should get the exact same number if you use ln for both of them. So this formula, this is called the change of base formula, and it allows you to get that exponent, that number, if the base is something other than 10 or e. Set up that ratio and choose the base to be whatever you want. But don't lose sight, this number, what does this number mean? 2.579, like if we did some calculations here, what's the meaning of that number in the context, 2.579? Yeah, Jared? Right, looking back at the original problem, good. What were we after in the beginning? We were after the exponent of 3 that gives you 17. That's what we wanted, the exponent of 3 that gives you 17. Okay, so I just want to practice a little bit. Can I borrow your book for a sec? On page 149. Open up your workbook to 149. So on those 2 pages, you don't have to read any of the text. I'm just going to pick off a lot of these little equations, and you're going to practice changing the form of the equation by first focusing in with a statement, with a written description of what exponent you're talking about. Okay, so I'm just going to go through and jot a bunch of these down. So like starting at the top. There's that one. There's that one. There's some here. Down at the bottom. Okay, and then there's a bunch at the top of the next page. Just going to pick some. Okay, so again, on all of these, the first thing you want to do is create a phrase, a description of what's the exponent of the focal exponent. That's what you want to do, create a written phrase. Whether you write that out or you tell it to the person next to you. From that written phrase, recreate a new mathematical statement that represents what that exponent is. So just like we've been practicing, just keep practicing. So these are scattered on pages 149 and 150. You don't have to read anything on those pages, just practice. Okay, so that you don't feel like a fool, everyone get a partner, everyone talk out the meanings of these exponents, and the meanings of these logs. Everyone get a partner, everyone's talking. Which one? Looks kind of funny.
I got the same thing. Yeah. Well, because it's 3 times. Same one before, so yeah.
Okay, so these first ones, we want to describe the exponent, write it as a log. So Corey, first one, what's the exponent? Can you describe the exponent in question here?
X is the exponent of 2. So it gives you 10.
Right, it's the exponent of 2 that gives you 10. So how can I rewrite x then? X is?
Well, X is 3.3.
No, how can I rewrite? If it's the exponent of 2 that gives 10, we have a way to write that, right? So how can I write that?
Log
Uh-huh.
2 to 10.
So it's actually base 2 of 10. Yeah, so that's not 2 to the 10th. That's a common misconception. Log base 2 of 10. Base 2 of 10. Or, again, the exponent of 2 that gives 10. All right. Next one. Joe, what exponent is this talking about?
It's about the exponent
Uh-huh.
of 5
Uh-huh.
that gives 1 over 125.
And so how can I rewrite that exponent?
So this should be log
Log
5
base 5 of 1 over 125. Cool. All right, let's skip down to this one. How about this one? A little bit different. Nadine, did you make progress on this one?
Yeah,
So what's the exponent in question?
it's A.
A.
Yeah, so it would be, was 1.5 log base B. I mean, log base 5.
So A is, first of all, what exponent is A? It's the exponent of?
5.
Exponent of 5. That would give what?
So it could be B over 1.
That's right. Right. Okay, so for these, you have to isolate this first. I didn't tell you that, but what did you think about it? If you have to isolate, for this to work, you've got to isolate that base to the exponent. So therefore, if this is our A is our exponent of 5, that would give what? B divided by 1.5. So you imagine divided by 1.5 first. Does it make sense? You got what I put in blue, you got to isolate that first. Okay, next one. So what's the exponent in question? Can you describe it? Jonathan?
For see the exponent of the 4 times the exponent of 2 equals 8.
Okay. So don't let this. So what is the exponent here? What is the exponent? Only t? What is the exponent?
14.
4t. So we can really, what we're saying is 4t is the exponent. Which exponent is it? 4t is the exponent of 2. That would give you m. So how can we write that as a log?
So for 2 log base 2
Base 2
and
of m. So here the exponent is an expression. It's not just the t, it's 4t. The whole exponent is 4t. Therefore, that's what we're going to set. That's going to be our log. It's going to be the exponent of 2 that would give m. So 4t is log base 2 of m. All right, now putting it all together. Justin, question? You want to do this one?
Yeah.
Tell me.
It would be the exponent 2, is that 2k?
2k.
2k gives us, the exponent 2k of 5 gives us cubed 3.
Right. So 2k is the exponent of 5 that would give q over 3. So how can we rewrite 2k as a log?
Log base 5 of q over 3.
What do you think? Nailed it. Okay, so 2k is the exponent of 5 that would give q over 3. All right, now these are writing without a log. Okay, so over here we're writing without a log. So how about Brian? Log base 9. So what is how can you describe what t is here?
So T is the exponent of 9 gives 1 over
He said t was the exponent of 9. That would give 1 over 81. So then you could rewrite that as?
9 to the t equals 1 over 8.
Right. So t is the exponent of 9. That would give 1 over 81. What is t? What is the value of t? Can you see it? What's it? -2, right? -2. Okay, how about this one? Same thing here. We've got to start by isolating the log. So what is the exponent in question? What is the exponent in question? This, Jared.
B over 3.
B over 3. B over 3 is the exponent of what? B over 3 is the exponent of 4 that gives 22. A little bit trickier. But you got to start by isolating what I put in blue. So what I put in blue would be equal to b over 3. And that's our exponent of 4 that gives 22. Okay, let's skip down here. How about this one? Let's see. Morgan. So this is a little trickier because we have a log and an exponent. But let's focus on natural log as an exponent. So what's the exponent in question here? K. All right. So if it's natural log, K is the exponent of what? Yeah, so this one's a little trickier. So K is the exponent of E. That would give e to the 2. See what happened? So you got to see this this can distract you. Don't let the e squared distract you. K is the exponent of e. That would give this. Therefore, e to the k is e squared. And k equals 2. Next one. Fuda. What's the exponent in question here? S. What exponent is S? So what's there? Not 1. Remember what that is? 10. So S is the exponent of 10? 1,000. So what's the equation? Is that what you said? S is the exponent of 10. See, logs you can read from left to right. The exponent of 10 that gives 10,000. The exponent of 10 that gives 1,000, sorry. In this case, S is 3. Last one. Brooke. Because T is what? The exponent? Keep going. Right, so it's the exponent of E, right? We know there's an E there. Exponent of E, that would give you 7. The exponent of E. All natural logs are exponents of E. That's what natural logs are. They're exponents of E. They're exponents of E. Okay, so let's put this to work. Look at a number in the homework in the back of this. Look at number 67. So we're going to put this knowledge to work. Keep going. Homework. What page is 67 on? 178. Page, work on number 67, putting it all together. So putting together our knowledge of logs and applications for exponential growth. Is this the problem you're looking at? We got the right one? Okay, go for it. If you solved something like this in the past, don't revert to try to remember the method. See if you can apply what we've learned today.
First one.
Okay, Alex, get me started. How can I make, what's the first? Got this function, f, and I want to know how many compounding periods t it will take for the investment to reach $1 million.
Well, you have to substitute f of t, which is your output, for giving you, which is
All right, he's calling $1 million an output, therefore he wants to substitute it for f of t because it's an output. Agree with that? Keep going.
and then you're gonna isolate your would be your growth factor.
This part, right.
Mhm.
How would you do that?
Get rid of your initial value.
Okay.
To the other side.
By?
Divide
We're going to divide both sides by the 4186.58. And what do you get when you do that?
I didn't do it, I kept it in fraction form.
Oh, you kept it in fraction form. Okay, fine, that's great. Anyone get a value for that? Just yell it out. Nice and loud. 238? Something else?
I got 221.7.
Oh, okay.
Oh, I'm sorry. I thought you meant for the final product.
Is it 238.9?
That's the.
Here we are. We need the value of an exponent. Which exponent do we need the value of, Nadine? Which exponent do we need the value of? The exponent of?
I mean, 1.025. T. Power T.
So what exponent do we want to find? What can you describe this exponent that we want to find?
Oh, the exponent of 1.025 to get to 2, 3.
That's right. So this is what we want to practice. The exponent of, I wasn't fair to you there. The exponent of 1.025 resulting in
2, 3.
and how can we, what mathematical thing do we have to write that exponent? What do we got? Hamid.
Log 1.025. And then 238.9.
Logs are exponents. Logs are exponents. This is the exponent of 1.025. That would give you 238.9, which is exactly what we have, right? How are we going to get a value for that?
Exact value or
Yeah, or, well, a good approximation.
222. I mean,
But how?
exact value is 221.9.
That's not exact. That's still an approximation. But how? The question is how. How did you get that?
Basically, I just used the calculator.
How did you use the calculator to get it?
Okay, I did log that number 1.025.
Thank you. Which wasn't? Is that on the top or the bottom?
No, that's on the bottom.
That's on the bottom.
No, it's not that.
So you used the menu you went into the menu. Okay, so there is a function somewhere buried in a menu that will just do this exactly. But let's just practice using the change of base. So it'd be log of
2, 3.
sorry over
1.
You could also do ln. You get the same thing. So this is using base 10. You could also use ln. And you got, Omar, you got 221, you said?
Yeah, 221.9.
So how many full compounding periods in order to get $1 million? 222. What if this was 222.1? If it was 222.1, how many compounding periods would it take? 221.1. Still 222, because if this is greater than 221, if it's greater than 221, then at the 221st compound period, we don't have $1 million yet. Questions? Okay, yeah, so here's the deal right here. Practice this. This is, if you've never done it this way before, I really want to encourage you to, this is about understanding what's going on. And there are other algebraic techniques to do this, but it takes more time, more steps. This is the very fastest way to get it done, by understanding what you're looking at. I'm just writing down the log that is that exponent. Okay, so now I want to do another example that reviews last Tuesday's material, and that is 71. So before we get to A, B, C, and D, I want to review and kind of talk about the situation. So last time we talked about, so don't put your mind on 71 yet. Last time we talked about two ways to represent an exponential function. We have our standard way that we've been working on for a couple weeks. What was the standard way to represent an algebraic function? Austin, you remember? You got it. You nailed it. A times b to the x. And what's the centerpiece of that equation? What encompasses? B. B, the growth factor, is what this is all about, right? The multiplier on output to get the next output. That's the 1 unit growth factor. Okay, but then last time on Tuesday, we came up with an alternative way to view exponential growth. Remember what that was? E to the, not e to the x, e to the kx. So it can be we can have the exact same function represented two ways. This is through our standard growth factor b, and now this is through k, which was our continuous rate. So let's talk about b. Does b give, or does b reflect the true percent change? Yes or no? Does b reflect the true percent change? So if we had the value of b, say 1.62. Suppose b is 1.62. Does that number reflect an actual percent change per unit? Sometimes. I say no's and I see sometimes. What do you think? This is B. Any yeses?
It depends if you're capable with the money situation. I don't think it was like depending if it was APR.
I'm talking about this. I'm talking about B and the A, B to the X. I'm talking about any application. Yeah.
In APR, it doesn't. If it's decay, it does. In other cases, it would.
Is it APR? Does it have to do with? Does B have to do with APR? So Patrick, what do you think? Is this? And what is the percent change?
It would be 62.
62%. This is what we started the whole unit with, right? We spent a week or two working on growth factors. B, the 1 unit growth factor. Absolutely reflects. This is true. So it reflects true percent change. It's not, it itself is not the percent change, it's the growth factor, but it reflects true percent change. Okay, that's the number we've been working with for the last couple of weeks. But then on Tuesday, we started talking about this number K. K was called the continuous rate. Does K reflect the true percent change? Or is it? It's a rate. Is it the true percent change? Remember, this one is not. Because this one is like APR. So it's like APR. And it's not true percent change. The idea is that it's the percentage such that if combined with continuous compounding, moment by moment compounding would result in the true percent change. Okay? So it's this number that when combined with continuous growth results in the true percent change. Okay? So how are B and K related mathematically? How are, looking at our two functions, how are B and K related mathematically? You know? This is what we talked about. Alex?
Isn't it through X?
No.
K multiplied by X will give you B.
Christian?
B is equal to e to the k.
B is equal to e to the k.
K is the K is the equal power to E that would give B.
Yeah, so he said B equals e to the k. Is that, yeah, that's exactly right, because our a's match up, our x's match up. What's left? The base for x. B equals e to the k. This was the key to the relationship between the continuous rate and this number that's really fat B. There we go. This is our relationship between this continuous rate number, like an APR, and the true growth factor from which we can get the true percent change. It's my experience that this idea does not stick easily with students. They have a lot of trouble. The success on the exam is very low. B is the true growth factor. It reflects the true percent change. It equals e to the k. K is the continuous rate, like APR, which does not reflect the true percent change. It has to be combined with continuous growth, and then it results in the true percent change. So that's a review from Tuesday. So we're going to practice this with a decay problem now. So we've got this function here. Which form is the function given in? F of n is I e to the negative 0.1316n. First or second? Clearly given in the second form, right? It's given in the second form. So what can we extract from that? What do we know? Given that function.
We know that k is minus 0.1.
Right. It's giving us the value of k, right? It's giving us k right there. K is negative 0.1316. So as a rate, as a percent, what percent is that? So the continuous rate is negative 13.16%. And our time period here is days, n is days. Is this the percent decrease per day? Is that the percent decrease per day? Negative 13.16%.
No.
I have 2 no's. What do you guys think? Another no. Is it the percent decrease per day? Another no. It's K. It's like APR, so they're all right. It's like K. It's not the true percent change. If combined with continuous compounding, it gives the true percent change. So let's do it. How can I want to get the true percent change of the size of the wound. How can I do it? Hamid.
Find the growth factor,
And how are you going to find the growth factor?
which is e to the power of 0.2316.
E to the k. So I'm going to go B equals e to the k, which is negative, as a decimal, 0.1316. Put it in your calculator. E to the negative 0.1316. And as soon as you get it, shout it out. 0.8 something? 67? What does that number mean? Who can describe? What is that number telling us? What does it mean? The what?
The growth factor for n days.
For n days? For 1 day, right? So this is a 1-day decay factor. And what does the 1 decay factor tell us? What is that number telling us? What's the 0.87 mean? 0.87 was what? How much is keeping? How much is kept? So the portion of the wound that, or this kind of like the percentage that the wound will be from the previous day. So if it was a certain size, the next day it will be 0.87 of that size. So what's the percent change? What is the percent change? How will we get it? Taz, I want the percent change.
This would be 13% change.
Okay, so how could you get it exactly? So you're
You subtract or you subtract that from 1.
right.
That should give it to you.
So yep. So we want 1 minus this minus 1, and we get negative what? 0.2 something, right? 1, 2, 3. Is the math right? So what percent by what percent does the wound shrink every day? 12.3%. So negative, the change is negative 12.3%. As opposed to the continuous rate, which was negative 13.16. So when you compound 13.16, after 1 day, the wound has truly gone down only 12.3%. When this is the part, there's a couple of questions on the exam. Extremely low success on this. So anybody have a question? Okay, so now I want you to do A and C. But I think most of you have 30% in your book. Is that right? To say 30% instead of 20? I'm going to switch mine to 30. Everyone switch it to 30. If you have 20, make it 30. So do A and C. Read C carefully. Don't just jump into calculating stuff. Make sure you know what's asking. So you're doing A and C. Come around once for questions. Okay, what's the function? What's the function part A? Did you get it? Taz?
Is it equals 300 times e to the negative 0.1316 n.
This is what he wants for part A. Is there another way to write that function? Someone do it a different way. Justin?
I said f of x is equal to 300 times 0.8684 to the t.
Wasn't it 8, 7
6, 8, or 6, 7, 6, 7, 6, 7.
to the n, right?
Or n.
Yeah. How about that? Right? Both ways. A, e to the k, n, a, b to the n. They're the same. They're the same because this is how we found that b. We took e to the k. Both are fine to use. All right, so part C. 30% of its original size. So we want the wound to be, not decrease 30%, but to be 30% of its original size. So how many square millimeters is that? 90. 0.3 times 300 is 90 square millimeters. Output or input? Output. 90 equals 300 e to the negative 0.1316 n. So now first step, so I want to isolate this right here. Okay, and therefore 90 over 300 first, which is 0.3 equals e to the negative 0.1316. Who learned something today? What's the next step? Tell me, talk it out. Who learned something today? Nadine.
I would log it. So we have log 0.3,
Okay?
log base 10 0.3 equal to negative 0.1316n.
Okay, so you're seeing this as the exponent.
Yeah.
And just describe in words what exponent that is.
The exponent of e to give 0.3.
Okay, so that's exponent is the exponent of e to give 0.3. And how do we express that? The exponent of e?
Log 0.3. Log base 10 0.3.
Base
10.
E.
Log base e.
E is not 10. And what is log base e?
Natural log.
Natural log. Okay, so what do we say? Exponents of e are natural logs. Exponents of e are natural logs. So we want the exponent of e that would give 0.3. That's natural log of 0.3. Last step to solve for n. N equals natural log of 0.3. We're just dividing by this coefficient here. Divided by negative 0.1316. How many days? Nice and loud.
9.148.
Okay, again, so are you comfortable in the middle of lots of things going on? Can you apply what we learned about logs? This is the exponent of e that gives 0.3. So it's the log base e of 0.3. So for Tuesday, you have a longer written assignment. That's predominantly what you'll have. But also check Blackboard for potential reading assignment and quiz. Okay? Have a good weekend.
Like,